Okay. So I think we did the one on the practice final, right? Last time?
Yeah.
Okay. So let me make up another one real quick. All right. Let's see. Let's see. Maybe I should pull one out of the book. Trying to come up with something that's not something we've already done. Yeah, the die we've done. I might be never married. It's true. All right, yeah, let's do one like sort of like this here. Business major, math major, chemistry major. What else we got? History major. What else we got? I don't know. I'm surprised they went beyond that. Psych, bio. Okay, that's one. So let's say at some college, these are the only majors they offer. Right, so if you wanted to be sociology major, too damn bad, don't go to this college. And they say, we think that they're evenly distributed. We think that the number of people in these majors is uniformly distributed. Let's say we feel number of students uniformly distributed amongst these majors. We don't think any major is really more sought after than another. Now, we know differently, especially as math people, we know this is true. Math is not necessarily a very sought after major. Now, the book uses this language, frequency, but hopefully you guys understand, frequency is what we observe. So on top of that, you can just put O for observed. Right? So say we look at 400 students, and we observe, well, this should be interesting, Jeff. Let's say we observe 30 in math. There's 1, 2, 3, 4, 5, 6. Okay, I like it. Oh, why did I do that? Let's make it something divisible by 6, just to make it nice. 600. So say we see 30 in math, 280 in business, 170 in chemistry, 80 in history, let's say 200 in psychology. So let's leave over first bio. Let's see. What am I trying to do here, of course? I think I'm already over 600, aren't I? Oh well, let's make psychology 100. Let's see, 310. Let's see, 200, 480, 560, 680. So let's make chemistry 80. I like it. So let's see, 160, 190, 290, 570. So this should be 30. All right, just to give us some numbers to play with. 310, 390, 470, 570, 600. Sweet. So it has 600. I like it. We don't let anybody be undecided. That's where things are headed right now anyway. And then we have the expected. Now, either the two main ways to do this, there's actually more than this, but the two main ways you'll see is uniformly distributed versus expected percentages in each category, right? The percentages, you just multiply each percentage by the total, and that's going to tell you how many you expect to fall into each category. Please, you guys, just let that make sense. Uniformly distributed, all you do is you take, in fact, if you heard me mumbling to myself earlier, you should know what to do to figure out what to put next to each of these. If it was uniformly distributed amongst these 6 categories, each one should get 100 students. I like it. So this I have to tell you. This I have to give you a way to figure them out. I like it. And then the formula, and you know, if you weren't here yesterday at the last time, it's very much related to the z-score formula. It's very similar to z-score and standard deviation formula. I'm converting into a chi-square score these observations I've made. Sort of like I convert into a z-score some data point that I collect. Same kind of idea there. Oops. So the observed minus expected squared. We square it because for the same reason we had to square for standard deviation, because otherwise that would add to be 0. Divided by each expectation. So I want a column of observed minus expected. Let's make that real quick. And now let's go ahead and make it observed minus expected squared. Just kind of cut to the chase a little bit. So observed minus expected here would be 180. And what's 180 squared? I don't know. Say again? 32,400. Yeah, okay. And then the difference here is 70. 70 squared is 4,900. Difference here is 20 squared is 400. Difference here is 20 squared is 400. Is everybody with me here? This is sort of like the charts we've already done. To be honest, it's actually easier than some of the ones we've done. This one is spot on. And then this one is another 70 squared, 4,900. Now I'm ready to add stuff up yet. Now, what do I need before I can add them up? I need a column of those. I don't have a column of those yet. So all I got to do is take that column and divide it by each expectation, which the expectation for each one is 100. Well, that's really, really nice. And if even it wasn't nice, you just got a calculator. Who cares? So I just kill off the last couple zeros. And then whatever that adds up to be. 6, 4, what is it? 430? 430, yeah. Let me stop there for a second. So you're going to have that formula on your sheet. As I discussed way earlier this semester, if you cover that, it tells you the column you've got to end at before you start adding stuff up. So I've got to get that column created before I can add them up. So my chi-square score is 430, yeah. All right, so now let's give us something to compare to. Let's say I want alpha to be 0.005. Does our chart go to there? Yeah, sweet, sorry. That was a big reaction, sorry. I was excited. Say alpha is 0.005. What is my degrees of freedom? Yeah, the K is 6. Degrees of freedom is K minus 1 is 5. So I don't care about the number of students. I care about the number of categories for this. And on your chi-square chart at the bottom, it actually tells you that shit. Because I forgot to cut that off. But it's there for you. Hey, hey. Okay. So alpha 0.005, degrees of freedom is 5. What's the chart tell me my critical chi-square is?
16.
Good, 16.750. And what's the chi-square distribution look like? Job of the hut, I like. You know, like a mound of taffy, and somebody just took one and just pulled it. It look like that. Big slug. So way up there. So my critical score was, what was it, 16.75? Yeah. Now again, a 0 would mean the only way to get a 0 here is if they were all 0. So a chi-square of 0 means it matches exactly with what was expected. Now this is a sample, so it's okay if there's some variation in the sample, and that leads to the same idea we had with hypothesis tests. It's got to be so damn far away from 0 that it's evidence that it's not 0, that it must be, there must be a difference. And we got to where? Yeah, yeah. We got over there. Yeah, we're way over there, right? Java's tail just goes over. I wanted somebody to go, I didn't see what you did over there. You guys, so we're way the hell in what? What do you think this is? Same as hypothesis test. Rejection region. So we can reject that the majors are uniformly distributed. We have found evidence to say that the majors are not uniformly distributed. And I would say it's pretty damn good evidence. Now there is a way with technology to find a p-value associated with that. It would be stupid small for 430. And that's nice for technology. But to me, this is what we can do by hand, and this is where you actually learn shit. Kids? Yes.
So your sentence would just be, we have found sufficient evidence that call it they're not uniformly distributed?
Yeah, we have found. Why have we found? Why do I want to say we have not found? Because I made it way in the rejection. I made it in the rejection region. We have found evidence that the majors or the students are not uniformly distributed amongst the majors. Yes?
Under what circumstances would it be where we have not found sufficient evidence to reject?
If it was here. If I got a chi-square of like 11, that is not different enough from 0. That's an allowable wobbly part because of the sample. It's the variance of a sample. I allow the sample to vary up to here. And then I go, no, that can't be explained by the variance of a sample. That must be a true difference.
Where did we get the 16.7?
Okay, let me put that up here.
The chart?
Yep. So the degrees of freedom, how many categories are up there? 6. So degrees of freedom is 6 minus 1. There you go. So let me see if I get it. Alpha is 0.05, sorry. So it's way over there, right? Stop at degrees of freedom of 5, 16.750.
And then if it's anything past that, obviously 430, and that's it, no?
Yeah, anything like 17 would be enough evidence, right? Anything beyond that would be enough evidence to say that they're not the same. 0 means that they're exactly the same, right? And then, to be honest, 0 would just mean the sample is the same. But that's pretty good evidence that the whole population is the same. As I move away from 0, that's starting to be like, And then for this problem, once you get past that, it's like, they're not the same. Because the further I get away, the more differences there were between the expectation and the observed. If that makes sense. The further away I am, the more important these differences are. So if I get past this, that's what we've set as the benchmark. That's enough evidence to say that they're not the same. They're so far away from 0 that they must not be the same. Oh. Do I need to put this up here? Let's see. So 0.005. And then you go down to 5. There's 16.75. Now, I also discussed, I didn't say you had to do this. I just said you had to do 11.1 and 11.2 from chapter 11. Right. 11.1, 11.2. That's the general stuff about chi-square and the goodness of fit test. 11.6 was the other possibility. That's got the other chi-square formula I talked about on Monday. And that's where you would use both sides of this. For like a two-tailed test or something, you use both sides of this. Just in case you're wondering. Because for us, for the goodness of fit, we're only going to use this part of it. We're not going to use that part at all. We're going to use this part. Okay. Okay. You want to do another one of those or no? Or did I give you guys? I don't even know if I have any extra. Yeah. Probably. You should have gotten this. If you got the correlation practice, on the other side is that chi-square practice thing. And it's got an example that's all done at the top. So if you missed out Mondays, you should probably have this handout. If you don't have one of those, just see me at the end of class. I'll give you one. Okay. So now we can, if you want to do another one of those, we can. We can move past that and start going backwards or actually whatever you want to look at now. Are there any specific kind of problems you guys want to look at? So glance over the practice final. Is anything kind of going like, I don't remember doing that at all? Or is that, if that's everything, just start asking about number one. You know. Problem one has got to be bread and butter. Problem one, what kind of problem is problem one? Yeah, you get a z-score, you look it up in the chart, you get the probability. What about the second part of number one? What changes in the second part of number one? Standard deviation. Good old central limit theorem. Becomes the old one divided by the square root of n. I like it. And then you do the same work just using the new standard deviation. So that's number one. That's got to be bread and butter. If I were you, I'd just find that and do it first thing. Number two is a little bit of a probability problem. I will tell you this. I might give you a problem like that, but I normally certainly give you a problem like that little contingency table we've done. You know, men, women, yes, no, or something like that. Or it could be a problem like this. I don't know. Haven't decided yet.
What's 1C again?
Oh, okay. Wait, what does that symbol mean, that big P? Percentile. So if I'm in the 95th percentile, where am I on the normal distribution? I'm way on the
Right side.
log it. And this would be how much?
35.
Yeah, there you go. So P95 means there's 95% below that thing. And so I'm just asking you to find a 95th percentile amount of money spent on coffee. This is actually data from 1999, if I remember correctly. I just haven't changed. I don't know, nowadays it's got to be way higher because the price of coffee is just stupid, right? Our coffee comes from, it tastes the same as this coffee. So screwed. Sorry. A friend of mine is a coffee snob, and I'm like, coffee, just coffee.
Okay.
Is that cool?
Yeah.
So that's the one that's reversed, right? Normally I give you an X score, you make it into a Z score, you look at the percentage. This one is you look at the percentage in the body, you find the Z score, and then you use that backwards formula to change it back into a raw score. You guys want to do that? Some of you guys like we did that this semester. So 0.95. What Z score would that be?
1.645.
Beautiful. So you just look up 0.95 in the body. You got to be careful. Don't look at. It's not 95% in the middle. It's not like a 95% confidence interval. That's not what it is. It's the Z score 95% below it. So you really want to look on the Z score chart, and that's a little asterisk dude. I like it. But you know what confidence interval would this be related to? What percentage is here? 5. So if I chop this off at 5, this would be related to 90% confidence interval, which is 1.645. So now that I know this, don't I also know the mean? I tell you the mean. Yeah. And now we know the Z-score. And I tell you the standard deviation. You just got to throw it in there. Work it out. Okay. So 9% of Californians believed back in May 2009, they believed that getting all children insured was not a priority. And you're like, who are these people? What? Yeah, kids, you know, they make it great. They're out there. So I would hope that you would have a really good idea of what kind of problem this is already. 9% believe that, so what percent don't believe that? 91. What kind of problem does this sound like? Huh? Yeah, PQ, binomial, NPQ problem. So if 35 California, hey, there's N. 35 Californians were selected, so what do I have here? I know N is 35, P is 0.09, Q is 0.91. I love it because these have to add up to be 1, no matter if they're wearing hats or not. And I want the probability that 4 of them. So what's the, and again, this will be on your little formula sheet. What formula am I going to use to figure this out? Yeah, cool. The N choose X and all that kind of stuff. I can relate. So it's this guy. Formula always makes it seem a little worse because it's got to be the most general. X equals 4, so this will be N choose 4. Yeah, 0.09. How many of those you want? 4. And how many of these you want? The rest, 31. Just this and this have to add to be this because that's how many people you got. And I just got to throw that in the calculator. What I love is when people try to appease crazy-ass Jeff and they throw a formula down that's not right, and then they use binomial something or other bullshit, and they get the right answer. Oh, don't do that shit. You better make sure, you know, the plug is this, so you make sure it's the right answer. I have no problem with you using buttons and all that kind of crap to check your work. But dear God, you better do your work. Whatever the hell that that comes out to be. What do you guys get for that?
0.1846.
Beautiful. Yep, 0.1846. Which means there's just over an 18% chance that we'll get 4 people out of 35 that don't think it's a priority to get kids on health insurance. Okay, it's a bigger priority to strip protections away from lands and stuff like that. Ooh, political. No, that's not good. If you're not paying any attention, then you're probably happy. Okay, all right. So number 4, what about the second part? 512 Californians are selected now. This is part A. Part B, N is 512. How do I figure out the mean and standard deviation? So if I were you, right now, I would have my formula sheet sit next to me, so I get used to finding stuff on it. Yeah, this is the best. So P is still 0.09. Standard deviation, of course, is beautiful. So if you're going to identify it as an NPQ problem, that has some of the best formulas ever associated with it. Right? Yes? You guys doing all right?
For
Yeah.
part 2, is it 1 or 2 standard deviations removed? It's 2, right?
It's definitely 2, yeah. Yeah.
You still use P from A, right?
Yeah, I really want this understood. If there's a 9% chance that somebody thinks this is not a priority, does that change just because I take a bigger sample? No. It's 9% chance that a person, I don't care if I pick 35 people or 512 people. That's one of the biggest mistakes is people think it's based on this. No. 11% of people are left-handed. If I take 80 people, do I suddenly change? I'm not left-handed anymore. What just happened? No. It's still 11% of people are left-handed. P can't change just because I'm looking at more people. Why? Maybe. That would be kind of neat. Oh my God. So again, I'm not sure how they don't feel. They'd have to be doing something going, ah. My writing looks like Jeff's now. Shit. So whatever that is. Right. Yes.
At the beginning of the semester, you wanted a certain number of decimal points for different chapters. Do you still want this for the test? Like at the beginning, you wanted like 4 decimal points, and then you went down to like 3.
So standard deviation's got to be at least. Oh, this explains a lot. And you guys got to be wondering why I keep taking a point off whenever you put your standard deviations down. It's because they have to go out at least 3 places, right? So if you go out 4 places, that's at least 3. I'm happy. If you go out 2 places, probability went 4. Why? Primarily because the z-score chart went out 4. And it's a good idea because then if you change it to percentages, you still have 2 decimal place accuracy for your percentage. So, and then the p-hat stuff, I wanted at least 3 places because that really changes it a lot if you round too much. So if you take everything out to 4 places, you're golden. So if I were you and I'm like, let me just make everything 4 places, appease this man so I can get out of this class. All right, so that's what I would do if I were you. Not a bad idea, yes.
Can you add in the max?
Yeah. So what did you guys get for the mean?
46.08.
And standard deviation?
41.9.
Oh, I lost my good. Yeah.
It's under this paper.
Oh. Jeff is messing with me. What'd you guys get? I'm sorry.
41.93. 41.
For this?
Yeah.
Is it really? Seems really big.
6.476.
Oh, you didn't? Did you score root it yet?
Yeah.
Do it again. 6.476.
476.
Yeah.
Coolness.
Yeah.
So now, like Raymond pointed out earlier, it's got to be 2 places up and down, 2 standard deviations up and down. So if you want, if it helps you, you could do 46.08 up twice. So add 2 of these. So 46.08 plus 2 of those. 46.08 minus 2 of those. Doesn't that feel a lot like confidence intervals? It should, because that's where confidence intervals come from, is this idea of going up and down to catch so much of the data. And then, you know, whatever that is in your calculator. So it's what do you guys get? What did past me get? Past me got, oh, I didn't even, oh, it's a good thing we're doing this. I didn't even put that on the answer key. So I get 59.032. 33.128. Right. So would it be unusual to get 60 people? Or yeah. If I got 60 out of 512, that would be officially unusual. How about if I got 59 people? Nope, it's in there, 59. I like that. And see, that's where people misinterpret things. This is just a guideline. It can't possibly be interpreted that exactly. If I get 60, is that evidence of something? It's evidence, but is it proof? No. Because there could be 60. In fact, I could pick 512 and all of them think that way. I could just randomly pick 512 people that happen to think that way. What's the chances of that? Very small. So that's why if that happened, I'd have to go, I think that study was wrong. That's evidence that they were wrong. It can't be. Is that good? Is that all right? Yes. Yeah. Have you guys, if you haven't done number 3 yet, let's go ahead. You guys try to do that. You've got your formula sheets there next to you, hopefully. So this one should be an obvious one, which formulas to use. And the first couple questions don't need a formula. By the way, I really want to make sure you guys understand this. On Monday, like I said, I'm giving all 3 finals. My morning final, my Math 90 final goes to 11:25. Do you understand? So I'm going to be just running over here just to get to the room. There's no office hours in there. So my office hours on Monday that apply to you guys will be 7:30 to 9:15. Because otherwise I'm sitting in a room giving a final. Okay. Oh, I forgot. Oh, Jeff. That was funny. Oh. I'm going to go ahead and give you guys the answer key. Yeah, we normally have about 2 hours for a test, so the final can't be longer than one of our regular tests, because that's how much time we have. Oh shit, I lost count. Yeah. By the way, real quick, I found an old answer key for just about the same practice final, which is kind of nice. And it had gotten to the point where you couldn't read the first number, and so I whited it out and I never wrote it back in there. So it's that first answer should be 0.1788. You might be able to see where I whited it out. It looked like it was 0.2788, so I whited it out. And I never wrote the 1 on top after it dried. So that first answer should be 0.1788.